Thank you. So I will be talking about mechanism design for automated market makers. This is a joint work with Hubert Chong from Hong Kong University and Elaine Xu from CMU. So Shri should already talk about some AMM basics, but let's do a refresher using my notation. Okay. In automated market maker, or AMM for short, we have a pool. Let's just focus on two assets today, X for apple and Y for cherry. Users can trade with the pool by swapping apple for cherry or the other way around. The price is determined according to some rules or invariant. Let's say, for constant product AMM, if we started with 30 apples and 10 cherries, then this curve, x times y equal to 300, captures all possible state of the pool. And by state, we mean the current amount of x, current amount of apple, and current amount of cherry. That said, effectively trading with this pool is just moving the state along the curve. For example, if I want to buy 10 apples, I will pay 5 cherries, put that 5 cherries back into the pool, and move the state to this new position. However, as we know, to submit a transaction, a user first submits it to a miner before it gets confirmed or executed. And this power allows the miner to exploit at the user's expense. For example, now if a strategic miner sees my buy apple transaction, it can put a buy apple transaction in front of mine, called front running, and a sell apple transaction after mine, called back running. The actual number here does not really matter. You can just trust my math. But now, because the front running attack drives up the price of apple, I ended up paying 40 cherries instead of 5 to get these 10 apples. And these extra 35 cherries all go to the strategic miner. And what's worse here is that the strategic miner is getting these 35 cherries at no risk. It does not pay any apple to get these 35 cherries. So such phenomenon that the miner uses its power over the block to exploit users is known as maximal extractable value, or MEV for short. So MEV has caused a lot of problem. As we just see, it exploits the users. And it also undermines the stability and security of consensus because it incentivizes the miners to fork the blockchain if the MEV reward it can gain exceeds the block reward. And also it leads to off-chain economy because these powers incentivize the users to form coalition or sign off-chain contract with the miners to get favorable positions. And this eventually will lead to centralizing effects, which contradicts our motivation to start with a blockchain, which is decentralized. So all these bad effects make MEV one of the most important challenges to address in blockchain nowadays. It would be compelling if we can eliminate MEV solely at the consensus layer. Unfortunately, this is impossible. So the recent result by Bahrani, Grimity, and Roughgarden in 2024, and the result by Ferreira and Parks in 2023 can be interpreted in the following way. Solving MEV entirely at the consensus layer is impossible, at least with respect to today's architecture. Meanwhile, there are many efforts trying to achieve strengthened guarantees at the consensus layer. For example, sequencing fairness, which guarantees approximately fair ordering of the transactions within a block, or encrypted mempool, which tries to hide the actual content of a transaction, so miners cannot look at the actual content of my buy apple transaction and decide their strategies. It is widely believed that these strengthened guarantees can help mitigate MEV. But little formal investigation has been put on the analysis of how applications like AMM can actually benefit. What exactly are the formal guarantees we can get from these strengthened properties? So this motivates us to ask the following two questions. First, instead of working solely on the consensus layer, can we rely on mechanism design at the application layer level to achieve provable MEV resilience? And second, how do these strengthened properties at consensus layer, such as fair sequencing, help us design mechanisms at the application layer? What are the extra formal guarantees we can get from these strengthened properties? In this work, we answer these questions with respect to AMM. And specifically, we designed a swap mechanism an AMM for two assets that offers two tiers of guarantees depending on the properties of the underlying consensus. So in the plain model, which captures today's architecture, where the miner has unilateral control over the block. So it controls the order of the block, it can censor user's bid. In plain model, we achieve arbitrage resilience, meaning that no arbitrager, no matter whether they're users, miners, or miner-user coalition, no arbitrager can gain risk-free profit, as in the attack we see at the beginning of this talk. If an arbitrager gains apple or gains cherry, it must lose apple. And this was also defined, also called no risk-free return in Ferreira and Park's work. Additionally, if our consensus provides a stronger guarantee of weak fair sequencing, meaning that the orders from the users are now sorted based on their arrival time, then we can achieve a strictly stronger property called strategy proofness, meaning that no strategic behavior can give me strictly better outcome compared to honest strategy. One thing I want to comment here is that sorting based on arrival time does not prevent front-running attack, and it does not just trivialize the problem. Still, an attacker with really small network delay can look at a victim's order, let's say my buy order, submit a front-running order, and as long as it has a small network delay, it can still enjoy a smaller arrival time. By arrival time, we mean when this transaction is first seen in the consensus. So the rest of this talk will be organized as follows. I will first formalize the swap mechanism in the plain model and explain how our mechanism works and intuitively why it achieves arbitrage resilience. Then I will explain what do we mean by weak fair sequencing model and how our mechanism achieves the stronger strategy proofness in the stronger model. So let's start with the swap mechanism. Okay. So in this talk, I'm just going to use this constant product AMM as an example. But our mechanism can work for general potential functions as long as that invariant function is increasing, differentiable, and concave. But in this talk, we will just use constant product for a better understanding. Okay. This is going to be the pool we work with, x times y equal to 300. We started with 30 apples and 10 cherries. Now, given any current state, the rate is defined as the absolute value of the slope at the tangent line of the current state. So this rate means how much cherries I need to pay per infinitesimal amount of apples. So this rate captures the current price. Now users submit orders to trade with the pool. And our orders contains 4 attributes. The first attribute specifies the type. It's either buy apple X or sell X. Second attribute is volume. It specifies the maximum amount a user wants to buy or sell. In this mechanism, we allow partial fulfillment. So if I submit a buy order with volume 10, I want to buy 10 apples. It is possible that I ended up only getting 8. Now, the third attribute denotes the acceptable exchange rate. So this is the worst price the user is willing to accept to execute its order. So for buy type orders, it means that I want my order to be executed as rate no greater than R. And for sell type orders, it means I want my order to be executed as a rate no smaller than R. And this last entry represents auxiliary information. It could be identity, could be submission time, could be arrival time, et cetera, et cetera. It could be used to sort the orders. However, in the plain model, miner controls the ordering. So in the plain model, a strategic user can submit multiple orders, not necessarily just one, and it can specify the 4 attributes arbitrarily as it wishes. And the strategic miner just controls the block. It can inject orders, censor honest users' orders, and it can sequence or sort the orders in the block arbitrarily. So how does our mechanism work? In the plain model, At a high level, it works in two phases. Phase one is a batch execution. So it executes a whole batch altogether, and the invariant is maintained at the end of the execution of the batch. So in phase one, we call it R0 netting. So it crossed the buy sell orders at R0 such that at the end of phase one type, either the buy type or the sell type, is cleared. And we're only left with a dominating type. And then in phase two, we will execute those remaining orders of the same type as much as possible. So let me use an example to demonstrate how it works. Let's say we started as an initial rate 1/3. Okay, we have 3 buy orders and 2 sell type orders. Since the cumulative volume of the 2 sell orders is smaller, we're going to clear all the 2 sell orders in phase one. Okay. In phase one, to do this, okay, to clear these 18 units of sell order, we're going to execute 18 units of buy order. For that purpose, order 2, which said I want to buy 11x at rate 0.5, will be split into 2 orders. The first one, buy x, buy 6 units of x at rate 0.5. And we call it 2a. And 2b is just buy x with the remaining units. Now we're going to execute 1, 2a, 4, and 5 all together. When we execute them all together at the initial rate R0, you can just think of them as canceling out. So these 18 units of buy orders trade with these 18 units of sell orders without needing to change the state of the pool. So at the end of phase one, 1, 2a, 4, and 5 are executed, and the pool state does not change. Now when we enter phase two, we're only left with buy type orders. And we're going to execute each one as much as possible. So for 2b, 2b can be fully executed. So it will move the state to this new position with a new rate being 0.48. Now for order 3 cannot be fully executed because of the acceptable rate at 0.75. Once we buy 5 units of x, we already hit that acceptable rate, and any extra part going over 5 units will end up with a worse price. So we will only execute 5x for order 3. So the submitter of order 3 only gets 5x at a price of 3y. So this is how the mechanism works. In phase one, it crossed the buy or sell orders at the initial rate, such that only one type remains. The type with smaller cumulative volume will be cleared at the end of phase one, and the pool state does not change. Then in phase two, we execute the remaining orders. In the example we just had, it's buy orders. We execute them one by one as much as possible. And by as much as possible, we mean that we executed it either till we hit the volume, like in 2b, or either till we hit the acceptable rate, as the case for order 3. So formally, this mechanism achieves arbitrage resilience in the plane model no matter how the buy and sell orders are sorted. The intuition is straightforward with our example because all the sell orders are executed as rate R0, 1/3, and all the buy orders are executed as a rate no better than R0. It will only get worse. So there is no way for an arbitrager to gain apple without losing cherries. However, the mechanism we just saw does not achieve strategy proofness in the plane model. Let's say if the auxiliary information was used for sorting, then in the mechanism we just saw, we know that the earlier I am in the sequence, the better price I can enjoy. So I would wish my order to appear as early as possible. And if this auxiliary information field was used for sorting, then users can lie about their auxiliary information. Or miners can censor honest users' orders to help its excluding user to get a favorable position. So this mechanism does not achieve strategy proofness in the plane model, but it does give us some intuition of what we want or what we need to achieve strategy proofness. we want it to be the case that users cannot appear earlier compared to the honest case. And this is exactly the guarantee provided by this weak fair sequencing model. So in the weak fair sequencing model, this auxiliary information will explicitly encode the arrival time, which in the honest case should be equal to the submission time plus the network delay. So in weak fair sequencing model, orders are sorted based on this arrival time. And users cannot underreport the arrival time. You cannot arrive earlier than you should, but you can delay your orders if you want. Also, they cannot modify honest users' arrival time, and they cannot censor honest users' orders, because now this sequencing is done by decentralized sequencer. As I mentioned, I want to emphasize again that this weak fair sequencing model does not prevent front-running attack. An attacker with small network delay can still front-run a victim's transaction. So for example, now the orders will be sorted based on their arrival time. I'm using integers here just for simplicity. By strategy proofness, we mean that no strategy is strictly better than the honest strategy, whereas an honest strategy instructs a user to submit only one order with its true type, its true demand, its true belief of the current rate, and its true arrival time. And by strictly better, we mean that within the true demand, subject to my true belief, I prefer to be executed as much as possible. For example, if I want 10 apples at rate 0.5, no worse than 0.5, then getting 9 is better than getting 8, as long as the rate does not go beyond 0.5. So formally, in the weak fair sequencing model, if the buy orders and sell orders are sorted based on the arrival time, then the mechanism we just saw achieves strategy proofness. Due to the time constraint, I will not be able to talk about the proof techniques, which requires careful analysis, but I think I can convey the intuition. The basic intuition, as we mentioned, being that users want their orders appear as early as possible, and the earliest they can be is with their true arrival time. Given this, once I fix my order, my position in that sequence, recall that the honest mechanism executes my order either till it hits the volume or till it hits the acceptable rate. That said, no matter what strategic order I submitted, I cannot get a strictly better outcome compared to my honest behavior. So to wrap up, in this work, we introduce a two-phase swap mechanism for automated market makers. In phase 1, we clear a batch and clear one type of orders. And in the second phase, we sequentially execute the remaining type of the orders. This mechanism achieves arbitrage resilience in the plain model, so there is no risk-free attack. And if we have a stronger consensus model that achieves weak fair sequencing, then this mechanism achieves strategy proofness. And in our paper, we also extend the model to another version called no short selling version, where users just prefer to buy or sell as much as possible as long as they have balance in their accounts. So there are many interesting open questions left by this work. We focus on the two assets case. How do we extend it to multi-assets AMM? And second, we achieve strategy proofness based on sequencing fairness. Is it really necessary? Can we prove that some form of fair sequencing is necessary, or can we achieve strategy proofness without relying on sequencing fairness? And the third would be, can we achieve an all or nothing fulfillment? Either my order gets executed or none at all instead of partial fulfillment. So I'll stop here, and I'm happy to take any question.
We have room for one question.
Interesting talk. My question is about, what's your trust assumption here? Like, how do these mechanisms get enforced? You mentioned it's going to be at the application level. So do you trust the application to completely enforce this? Or how do you look at cross-application interactions where some of these transactions come from multiple applications?
We view it as this mechanism executed by smart contracts.
Okay, thank you.